Hello, everybody. Welcome to the 53rd. Okay, let's do this again, I guess. Hello, everybody. Welcome to the 53rd instance of our SBCLB cast. It's wonderful to announce that we were able to get Mark Silberstein from the Technion Institute to speak here. He's an old acquaintance, and it was actually great to visit him in Israel. And I hope to do this soon again. So now Marcin is going to introduce him in more detail.
Thank you, Torsten. Mark is a professor in the electrical and computer engineering department at Technion in Israel. His projects have been published in top system venues, with some winning awards and others being adopted by the industry. He regularly serves on the program committees of leading system conferences, including as a program co-chair of Eurosys 24 and ASPLOS 26. Without further ado, the stage is all yours, Mark.
Thanks very much, and thanks very much for having me. It's a pleasure. As much as I wish I were in Zurich now, it's okay for now to just give a talk virtually, hopefully to catch up later. Right, so this talk is sort of a retrospect on a past 10 years of research that we've done in my lab, Accelerated Computing System Lab. And I titled it Accelerator-Centric System Design Past, Present, Future. The majority of the talk, the major part of the talk will be about the past, and then maybe about a third will be about future and the present part. All right, so let's get started right on it. Modern AI training servers. Those architectures have been published all over, and people are ready to pay zillions of dollars for that. So how do they look like? On the left is an NVIDIA system, a recommended NVIDIA system with 8 GPUs, NVMe drives, and a DPU, which is a smart NIC, or in other words, a NIC with a network device with a processor on it to run some stuff. And on the right-hand side, there is it's an AMD system, which is remarkably similar in terms of all the provisioning, all the hardware. And I will focus on NVIDIA one because it's just easier for me to talk about it. Most of my work has been done on NVIDIA systems. So let's take a closer look. This is what we call an omni-programmable system. What I'm trying to say here is that this system has been dramatically more programmable than the systems that we used about 15 years ago. You can see that there is these clouds of programmable logic and NVMe SSDs and SmartNIC and GPUs. And one can, have this feeling of programmability basically scattering over from the main CPU to the peripherals, to SmartNIC, NVMe, and GPUs. Of course, not all these components are programmable by the user. For example, in NVMe, it's still rare to see programmable logic that can be used or changed by the users of the system. Yet, there are already devices that allow programmability for storage as well. So, what does it really mean for applications? Okay, let's take a closer look at a typical application that we all happen to love for the last 5 years, or maybe a little bit more. Inference, machine learning inference, and this is a very simplistic example, but still pretty representative. You have a client that accesses some server to perform inference on images, and those image and the actual function that is being invoked is neural net inference to recognize digits. That is the venerable MNIST network. So the way the server would be implemented is by serializing the request that is received from the network, loading the right ML model for the specific task, processing the task on some processor, and then deserializing the response and sending it back. So as a matter of fact, Oh, now I figured that I have a mistake in my slide. Of course, deserialization and serialization should be switched in places, but that doesn't really matter. I guess you got the point. Now, this color code here is for signifying where the specific task should be executed. And as you can imagine, the NIC is very good for serialization and deserialization because data is passing through. And SSD is great for processing the ML model before it's being loaded in some format onto GPU, and then the GPU will be used to process that that task. Okay, so far, no questions, I guess, unless there are, and I'm ready to answer. Good. So as you can see, there is no CPU in the loop. As a matter of fact, CPU should not be used at all. In any efficient system, CPU would do something else. Okay, and all the real stuff would be done by the NIC, SSD, and GPU. So the ideal execution sequence would be to serialize or deserialize the request, to load the model, to process on GPU, and then eventually deserialize. Okay, so there should be some kind of data flow like this. In practice, however, it looks very different. And the reason why it looks very different is because today, in order to receive data from the network, you actually have to have a socket or QP or whatever you have, whatever interface you're using to receive data from the network. And then at that point, you would want to push the data received in the CPU, apparently, back to the NIC in order to perform deserialization. I don't think that this is a very wise use of resources, but we wanted to see how one would implement the server, and if we really want the compute tasks to be mapped to the right processor, this is what you would have to do. You would have to ship the data back where it was actually already before. But again, you would have to receive the data using the operating system abstractions like a receive call. And so you already got the point. In order to load the model, you would have to read it from the disk in the CPU, because that's again where you have a file system. You would have to copy it to the GPU, then copy the response back and send it back. And again, the deserialization process, or again, sorry for the mistake, serialization would have to be done on the NIC only after we first push the data to the NIC. So this is really a kind of very inefficient way of using the resources, as you can imagine, because there are a lot of data movements that should not have happened. And the only reason why we are seeing this is because CPU is the only one that has all the right abstractions to run these data flow, right? So you don't have sockets or isolation or transport layer on the NIC. You don't have files on storage. You don't have native execution abilities in GPUs, implying that you cannot basically run GPU standalone without having any CPU context in the background. So there are fundamental limitations of modern systems to actually implement the data flow that we outlined earlier. And the key reason is that CPU is the boss, right? You realize that everything that is happening in the system is under CPU's control, and not only the control, but also the data is always going to be on CPU one way or another. So the idea that we've been pursuing for the last 10 years, more or less, is outlined in the vision paper called Omnix. And was published in PhotoS in 2016. And this paper basically tries to put together a vision of a accelerator-centric operating system, or more generally speaking, accelerator-centric system design that would allow us to effectively eliminate all those inefficiencies that I mentioned earlier, and allow building systems that are entirely CPU less, okay? Or to some extent, not using CPU at the level of intensity and with all the overheads that we've seen before. So in Omnix or in this kind of design, you still have CPU running the regular operating system, so you don't really get rid of CPU altogether. However, every one of those processors, GPU, NIC, or SSD, will effectively run some operating system services that are optimized for that specific processor, for that specific architecture, and they interact with the operating system on the one hand, but also enable each one of the processors in the system to behave as if it was a regular processor, allowing that processor to invoke tasks on other processors and perform I/O directly. So the key design principles behind Omnix are as follows. As I mentioned, each accelerator runs an optimized library operating system, and underneath this library operating system optimizes the control and data path the way that best suitable for a particular application as well as a particular hardware. And in addition, all accelerators or all processors in the system, as again, I mentioned NIC and SSD as processors because they, as I mentioned earlier, already run certain logic that can be programmed in theory. So those accelerators invoke tasks and perform I/O directly with their peers without CPU mediation. So why don't I like CPU so much? The reason is that CPU mediation actually is a problem. It is a problem because the latency of interacting between accelerators is higher. It is because CPU becomes performance bottleneck whenever GPU wants to send data to another device. It so happens that it interrupts the CPU and does a lot of interruptions for the CPU to do that. So that becomes a performance bottleneck when you want to scale to more GPUs. The scalability is poor, as I mentioned, and last but not least, from the system's perspective, if you have different tasks, all of which are running entirely on accelerators, or at least in theory, but have to use the CPU, the central CPU, for I/O and other activities, then the performance isolation between those will be actually pretty bad. Because, for example, one GPU needs to send a lot of data and another needs to send little data, but at lower latency. And you can imagine that the GPU sending a lot of data will effectively collide with that sends less data and eventually potentially win. So there is a problem with the CPU utilization fairness here. All right. So what is the role of CPUs then? Yeah, do the setup and leave. In practice, however, this is not really possible. So in order to really build something like that in the system today, you would still need to have the CPU actively involved in exception handling and allocation of resources and cleanup and privileged operations, because all the rest of the system usually, for example, GPUs do not have privileged execution at all. And also, the CPU will be the one that would run the main program that effectively would create this software context for the rest of the processors in order to be compatible with hardware drivers today. So what I outlined here is the vision of the system that is supposed to be very efficient to build when building the kind of applications that I outlined earlier. And over the years, we worked quite extensively on different aspects of Omnix, or accelerator-centric design. And again, it's a kind of interesting that Omnix as a system never really materialized and probably will not materialize. But different components of that system were effectively implemented in different forms, with particular focus on GPU interaction with I/O devices, but not only, also a variety of GPU abstractions to talk between themselves, as well as the use of SmartNIC And finally, integration of NIC interfaces with hardware accelerators. I will not cover those issues in this talk. I will primarily focus on the first two. And I'll start with the file system storage access from GPUs following the accelerator-centric design. So it's a good point for questions if you have one. Good. All right. So if everything is clear and I convinced you that there is a case for this kind of approach, so let's see if it's even feasible. So the first paper that basically started this all, I wrote it in 2013 and published it in ASPLOS back then. And the key idea of that paper was how do we allow GPU kernels access file system directly? What it means is that any GPU kernel would be able to open a file, read and write the data, and close the file, and perform all other file operations using file names and directories and whatnot. And what is really important here is that it will fit the big picture of one large system, so that CPUs and GPUs in the same system would actually see the same abstraction in terms of the files, right? So there will be the same kind of well-defined data consistency. There will be the persistent optimization. And last but not least, there will be optimized data locality and reuse, right? And we all know that the CPU operating systems are doing a great deal of a job for optimizing the locality with a page cache and performing a variety of optimizations for buffer management and prefetching, et cetera, et cetera. None of this was available for GPUs, and we thought, why not we introduce those in GPUs as well. So this is the example of a code that runs inside GPU. For those of you who have a little bit of experience with GPUs, you would notice the __ shared keyword, which implies that this is a buffer in the GPU shared memory. So this is only this code can be only invoked on GPU apparently. So you can see that the code looks very much like regular file accesses with opening files and reading and writing and closing. And again, I'm not going to get into the details, but basically this is the feel of the system that we wanted to build and built eventually. The system itself looks possibly pretty complicated on the slide, but let me kind of briefly skim through the key aspects of that system. So first of all, on the right-hand side, you can see the library that is actually implementing the file system abstractions for GPU programs with massive parallelism. And while implementing it, there was a need to understand how to enable GPUs not to contend on locks and basically make this kind of interface massively parallel. On the left-hand side, you can see a variety of blocks that we had to implement in order to allow the CPU to coordinate the access to files with the GPU. So by that, effectively implementing the distributed page cache, which defines the file system consistency semantics and provides a well-defined abstraction for the file access on both GPU and CPU. So those are the key components. And let me just give you a little bit more detail about the core part of the system, which is this system-wide page cache. And this page cache effectively allowed us to implement a sharing between file sharing between CPUs and GPUs or multiple GPUs in a very systematic and well-defined way, effectively implementing software-managed consistency underneath. This was a lot of fun, as you can imagine, because it required a whole bunch of synchronization primitives to be implemented between CPU and GPU. And at that point, even GPU developers and NVIDIA itself didn't really understand the consistency semantics of memory accesses over PCI. So it was a little bit of a mess. But eventually we managed to do that. And why would one use this kind of thing? So here's the application that we implemented using GPUFS. This is an image collage application. You have a bunch of files with images, and you want all those images to be placed on some kind of a large image as a collage. Okay, so this is what you can see on the right-hand side. In order to build this kind of things, you have a lot of files to be processed with the images, right? And there is a lot of processing to be done in order to make sure that this image actually looks coherent with the background or with the base image that you are trying to match and map it on. Okay, so what is so interesting about this application? The key aspect of this, what makes it particularly important and particularly suitable for GPUFS is data-driven data accesses, right? You don't know which files to access before you already process some prior files. You can't pre-process everything unless you're going to waste a lot of compute time. So the data sets are huge. They don't fit the GPU memory. And the only way to actually run it properly is through this data-driven access pattern, where the GPU figures out what to read next once it knows what kind of background is expected and what to process there. And importantly, this design allowed us to run 3x faster than any traditional design that we could implement, and we really tried very hard to optimize the baseline. That was the best baseline we got to. All right. Okay, so GPUFS was a great success in our view because it basically introduced this whole concept of operating system abstractions on GPUs, but quickly enough, we realized that there are quite a few challenges left, and the challenges were related to the usability of the system. Actually, when we built the system, we thought that if we expose file system abstractions to GPU programmers, they will love that because these are familiar abstractions. Turns out, GPU programmers don't want changing their GPU code to access files, and what they actually end up doing is pushing files from CPU to GPU. This was much easier for them to build. And another problem was that GPU library OS, the one that implemented all those abstractions, consumed a lot of GPU resources and effectively slowed down the real applications that wanted to use it. And last but not least, CPU was still involved in the control path because the disk accesses were performed on the CPU. So the question was, could we do better? And the answer is yes. And for that, we need help from hardware. And here I need to do a little bit of refresh for everyone here to remind what memory mapped files are, because this is the abstraction that we are going to implement on the GPU. So memory mapped file is basically the way to access files by mapping them into memory and then accessing that memory as if it was a regular memory, though it is backed by the file. Okay, so you can see that I have this file here. I map it into memory, and then I can update it or read from it, and effectively it will be written or read from file, but not from memory. Okay, so for that I have this mmap and unmap system calls. Right, so our goal was to leverage GPU page faults and effectively implement memory mapped files inside GPU without having to change the GPU kernels in order to in order to access files. So under the hood, GPU page faults triggered CPU logic that basically created the read call from file, very similarly to what CPU page faults do. and access those files and put them into GPU memory. And this was great because you can imagine that here you could possibly just map the whole, I don't know, input and output through mmap, and then keep the original kernel without any change. So GPU page faults were invoked or basically triggered automatically by the GPU. And so this was great, but not everything was that easy because it turns out that files can be not necessarily in a disk, but they can be in memory or used as well by the CPU. So how do you coordinate and how do you synchronize access between CPU and GPU? Well, turns out that we had to implement a new consistency, well, not new. We had to relax the consistency model of the page cache in the regular operating system, and we implemented the release consistency model to allow GPU and CPU access the same file and synchronize later. Okay, so long story short, this is the CPU code that allows one to map a file on GPU, and then there is a GPU kernel, and this GPU kernel just runs and makes sure that it accesses the data. Once it's over, there is the release call, which effectively allows one to synchronize the data back and then access it from the CPU as well. So this was a neat idea, and it really created nice results in terms of performance. It was much more usable. However, we were still facing some other challenges. GPU page faults, turns out, is one of the slowest logics that you could have. They slow down, not only they themselves are slow, implying that file access or IO is actually slow, right? But they block a lot of GPU logic on the way. So they have a pretty significant collateral damage. When you have a CPU page fault, usually only the process that causes the page fault is affected. In GPU, because there are so many memory accesses, you have an avalanche of page faults, and those page faults need to be all handled by the CPU. So eventually, you end up having a pretty significant overhead. Right. And so it turns out that GPU programs are mostly regular, so they're not data-driven, and it's not worth paying the price of having this very flexible abstraction. So the simple way to do it is just to access data before the invocation, and the only thing left to do for us as operating system people is to optimize the data path. Basically, directly move data from SSD to GPUs and back. So this is actually a very plausible hardware, in a very plausible way to use modern hardware. There is this thing called peer-to-peer interaction between GPU and storage, and it is already it's been available for quite a while in hardware, but not exposed to the software. So our idea was, why don't we enable the CPU? Why don't we add the system calls that instead of accessing buffers or instead of keeping buffers in the CPU memory, would also allow directly addressing buffers in GPU memory. So think about it. You're just going to read data from the disk, and instead of CPU buffer, you will specify the GPU buffer. How great would that be? Okay, so this is already not GPU initiated system calls, and so there's no overhead on the GPU whatsoever, and yet the data path is accelerated. So this is great. Turns out this is not that simple, because existing systems that, well, at least at the time when we started implementing this, they had very narrow APIs and very hardware specific. They were not generic. It was difficult to optimize performance. There was no integration with the file system. And again, consistency semantics, right? What if the file is not on the disk, but in the page cache of the CPU? Then you cannot read it from the disk because there is a newer version in CPU memory. So with that, we implemented the spin, which was the kind of system that allowed full integration of this idea of peer-to-peer data movements into CPU page cache, and it allowed GPU-aware prefetching, and it was compatible with block layers. So it had a lot of important parts that were unrelated to performance per se, and they were pretty generic from the operating system level perspective. So with this, I mostly covered the key contributions in the storage land, and now let me switch to the networking part. Unless again there are questions, so it would be a good checkpoint to make if you want. All right, so let's move on. Then let's talk about networking abstractions. All right, so just a little bit of background. If you want to use RDMA NIC in your system, or it used to be the case many years, right, until this was fixed finally, what eventually you would need to do is to effectively run some CPU logic that would interact with the driver, and it would effectively pull the data from the NIC and push it to the accelerator. And if it wants to move data from the accelerator, it would go the other way around. Okay, so that's easy, but very inefficient. Okay, so what can we do? Well, we all know GPU direct RDMA. This is the technology that was announced by NVIDIA, and actually not only by NVIDIA, there was very similar technology in AMD, where the data path was entirely direct, which is called zero copy, where the NIC would DMA data directly to the accelerator memory. And but still all the control would be on the CPU. And so why this is bad? Well, we already understand that we have this problem of data-dependent accesses or data-dependent logic, where you would want to initiate I/O directly from accelerators. So you would really want to run RDMA code, RDMA calls from GPU directly. Okay, so why is that? RDMA is usually used for latency sensitive applications, and if you're going in your control path through the CPU, this actually increases the latency quite significantly. But there are a whole bunch of other issues that make the use of GPU memory but CPU control pretty awkward to use. So the first shot into this direction was using GPUNet. This was an attempt to implement the full GPU socket layer on entirely in GPU, so that the green rectangles are on the right. You can see in the middle those that allow basically to run all the API that you used to run on CPU only on GPU. And a lot of work was put into making this abstraction as efficient and convenient, while under the hood, CPU was only used to control RDMA NIC, but all the data was directly moved to the GPU. But what was really important in this case, that the GPU was the one to manage the buffers. So it was much easier for the application developer to manage these things. Now, really, CPU was involved in the control path for RDMA protocol for InfiniBand, and also in both control and data path for TCP, because it was impossible to implement the TCP transport on GPU efficiently. And even with that, we still achieved pretty significant speed up in terms of running real network servers on GPU. And the truth is that it even surprised us ourselves. The fact was that without this abstraction, GPU was even slower than CPU for those servers. So this was a big success. We showed that using GPUs might be beneficial in the cases where it was believed that it was not beneficial at all. Right, but this was not enough because we really wanted to get rid of the CPU and the control path. And then this was the follow-up work with porting RDMA entirely into GPU so that RDMA execution and control was performed entirely from GPU. Okay, you can see the CPU was entirely idle throughout this whole operation. However, even though GPU RDMA improved performance, and we can see a lot of nice numbers here, there was one big problem, okay? And the problem was that when the GPU was trying to send data over RDMA, it turned out to be very, very slow in terms of collateral damage, I would call it, right? Because GPU was supposed to access the NIC over PCI, and this access was extremely costly and affected a lot of GPU threads. Very similar to the page fault, as a matter of fact, but very different nature, of course. Then we figured out that RDMA verb creation was very costly, and so doing that on GPU was a very bad idea. And last but not least, it worked only for hardware offload for RDMA, but not for TCP. So we tried to solve those issues, and the solution came from SmartNICs. And the goal was to enable accelerated networking with minimum overhead for the accelerator itself. Okay. And as I mentioned, all prior attempts actually imposed pretty significant overhead on GPU programs themselves. So we tried to understand how we can get rid of that. Just a reminder what SmartNIC might look like. This is a real SmartNIC, with the diagram of a real SmartNIC called Bluefield, and produced by NVIDIA. This SmartNIC has a regular NIC ASIC. But in addition to that, it also has an ARM core which runs Linux. Okay, it's actually very weak ARM core. It runs about 6 times slower than the regular x86 CPU core. So it is really difficult to match that performance of any application you would want. With this ARM, it's usually used as a controller of accelerators that are sitting on the same on the SmartNIC, but not as something that would implement some heavy logic. So the idea that we implemented in our work was to effectively use this ARM processor for doing the heavy lifting of network stack, and effectively implementing the cookie, what is called the completion queue and work queue in a custom way, so that the accelerator and the GPU in this case, but not only, we also have it for another accelerator too, so that the accelerator would not need to do anything. It would just store the queues and the doorbell, which signifies to send data out. It would store them inside the GPU memory or accelerator memory, and all the logic of understanding what it is and how it looks like was entirely offloaded to this ARM CPU. Now, importantly, this approach shows that if you have a weak controller and you can offload the heavy lifting of I/O operations that are pretty significant in terms of sequential load, but they cannot be easily parallelized and they're latency sensitive. Doing that on the accelerator, on a parallel accelerator like GPU, is a really bad idea. But offloading it to that ARM that is weak but still much more powerful than the single GPU thread, it's actually a good idea. And we show that you can scale this design to multiple GPUs and even hold multiple up to 100 GPUs on a single SmartNIC. So this work really showed that we can run a very large number of GPUs. We can manage them. We ourselves built a cluster of 12 GPUs, but we project to get to 100 with no scalability issues. So, all right, so at this point, I want to kind of take a pause and say, okay, this is what we've done. Okay, we've been working very hard and tried different ways of optimizing data path and control path and allowing the accelerators to work well with the IO and with other accelerators. What did we learn? Okay, so we learned that Omnix is great, but for a very narrow set of applications, because there are much simpler and potentially more efficient solutions for other types of applications. So whenever you have an application that has a irregular data access pattern that is data driven, this is the only way. But when it is not, probably there are easier ways to do that. Okay, so the adoption has been very slow. What actually was more adopted, and I will show it a little bit later, is the way to optimize the data path alone, effectively providing the means to perform data path optimization that I mentioned earlier with GPU RDMA and with the SPIN project. So those were largely adopted, and I will mention it later as well. So just a brief kind of note how people deal with IO overheads today. Turns out that in ML, which is the primary workload for GPUs, there is a predictable and static control flow. So you can actually build a graph of all the kernels and all the IO operations you want to do, and it's entirely predictable. And once you build it, you just upload that graph onto GPU and push the button, and GPU itself has a specialized processor to efficiently execute this graph. And so what we actually have here is, in a way, another alternative for a very common case, yet we already understand here that conceptually speaking, this is not very different from what we proposed, only that there is a specialized processor used to perform all those operations on GPU and basically hide all the latency and overheads associated with IO accesses. So this is what people do today. However, let's take a look at let's take a little bit broader look what happens in the world in terms of the impact of our research on the landscape of accelerated computing today. So first of all, NVIDIA has this Magnum IO stack, which has storage IO and network IO accelerators for GPUs. And GPU Direct Storage was introduced in 2009, 2 years after we published our work, which is remarkably similar in a variety of aspects, yet potentially more stable, I would put it this way, and also ignoring a lot of complications related to page cache that we thought were really important. And these guys decided that this is not as critical for the product. But the core of the system is actually there. Similarly, there is this NVSHMEM library that allows GPUs to share memory and basically provides the open SHMEM kind of abstraction for those of us who played with high performance computing. You probably are aware of this. Interestingly, the first implementation of SHMEM entirely in GPU was in the 2016 GPU RDMA paper, where we showed that this is actually a good idea. We didn't have access to NVLink at this point. Eventually, this became the library that allowed the NVSHMEM works on top of NVLink. But again, the concept was already introduced way earlier by our work. So these are sort of things that were adopted by NVIDIA. And there are a couple of startups here in Israel which are effectively taking much more avant-garde ideas with CPU-less inference servers on custom NICs. This company is called Neurality. And another one called Plyops, where they do GPU-initiated access to storage, and they claim that this is a good idea in terms of cost and performance. So, I'm actually coming to a conclusion of my talk, and I foresee bright future for accelerator-centric design. I actually think that the time is becoming ripe for a full-fledged accelerator-centric system design because CPUs are getting more coupled with the GPU, and this is already the case for the very recently announced NVIDIA Grace Blackwell superchip. And you can see that CPU and GPU are integrated. And what it means is that we will allow much more tightly coupled and GPU-enabled I/O abstractions that we should think how we would design. And it seems that the idea will be to decrease CPU overheads due to I/O processing because CPU will be heavily used to manage this beast. Okay, so you can imagine that you really want CPU to be busy with invoking GPU kernels rather than doing some I/O. So presumably we are coming to the architecture that will make accelerator-centric design even more relevant than before. And I will skip that part because apparently I don't have time unless, I can extend for 2 more minutes before I will take questions.
That's not an issue. Go on. It's fine.
Okay, so one interesting twist in this story is that the same idea, or I would call it the same concept of accelerator-centric design, is directly applicable to modern data centers, where, of course, the idea is the same, but the context is very different. So let me kind of explain what I mean. For data center architectures today, the resource disaggregation is becoming the thing of the present, not even the future. So you can see that the servers are broken up into pieces with CPUs, GPUs, accelerators, SSDs, and memory all sitting in different places. And basically, the actual server is built on demand from all different places on the in the system. Okay, so this is all great, but how do we go about using this hardware efficiently? So the first approach that people are using today is what is called remoting, where the unmodified CUDA application would be there will be a special library that would intercept all CUDA code, all CUDA calls, and would basically transfer that to the remote GPU. So this is great. It works very, very smoothly, but very, very slowly. And here's the reason why. Okay, the reason why it is running so slowly is because if you think a little bit about the more complicated application, where you have more than one item, but actually multiple elements that interact with each other, and again, I'm going back to this inference server, you would need to use CPU to invoke everything, as today, again, in the standard design, that's what you would do, right? But now imagine that you are going to distribute it across different racks. So you can already see that the amount of memory copies that are going to be involved here is tremendous, and all of them are entirely redundant. Because what you really want is for the CPU to go to GPU and then to go to the NIC or vice versa, or to storage, right? So without actually taking all these paths through the cloud. So you can imagine that this is really inefficient. So what we really need is this kind of peer-to-peer system where the CPUs and SSDs and GPUs can talk to each other directly. So how can we do that? Well, again, this is the problem as we identified. And then the question becomes, okay, how can we fix that? Okay, and the way we can fix it is through the use of specialized SmartNIC, which runs a specialized operating system that exposes the abstractions to leverage devices with peer-to-peer interaction, effectively build this kind of data flows that we need to build here. And the way it works is that basically the CPU asks the SSD to invoke GPU on the data that that the GPU wanted to read, then GPU would return the data to SSD or back to CPU. So you can see that the data is flowing around without having to go to the centralized location, and all the control is also distributed. So this was an experimental system published in 2022. And as you can understand, the conceptual contribution of this is to basically map the Omnics design into distributed design. So to summarize, in the past, we did a pretty systematic study of design trade-offs for building accelerator-initiated I/O abstractions and accelerator-centric design per se. And at present, we believe that people are kind of gradually adopting some of these ideas. Pragmatic ones have been used by NVIDIA and AMD, and more advanced ones are by startups in the area. And in the future, it seems like new hardware trends really change the trade-offs and call for novel designs of I abstractions, and the way to build this kind of system is going to change, of course, and there's ample opportunities for research here. So which brings me to the last slide, almost one before the last. As a matter of fact, this line of research kind of died out in 2022, 2023. And we are really working a lot on programmable networks now and on confidential computing. So if you are interested and you have curious what we're doing, all the papers are on this website, and we'll be very happy to collaborate on any of those directions. And that is it. So this is my group at different times. On the right, this is COVID time when we traveled around and climbed some mountains to have fun together. And on the left, a much more formal gathering where we presented our activity at the department. But you can notice that there are quite a few faces that still remain. So yeah, the people stick around. With that, I'm very happy to conclude, and thanks for your attention.
Thank you. Thank you, Mark, for the great presentation. I'll take the time to let you know about the next BCAS, which will be happening on the 12th of December by Jesper Larsen Treff. And will be actually the first in-person BCAS that we have scheduled. With that, we will take questions now. So if you have any question, you can either put it in the chat and then I'll read it out, or you can raise your hand and I will unmute you. So maybe a quick question from me first then. I'm actually interested, what is the reality at this point in terms of CPU-less designs? So how close is it to being real, and how far are we in terms of timeline and in terms of technical design, practically speaking?
I just want to make sure I understand the question. So you're asking how far are we with the GPU-centric designs in terms of practical implementation?
Yes, in terms of, do you think that there could be entirely CPU-less design, where, for example, we have just the NIC and the GPUs, not really having,
Yeah, I understand. So again, and let me go back to this slide. So these guys are exactly doing that. Okay, so basically the first the neurality is trying to get rid of the CPU and basically have deep learning accelerators, DLAs, all managed by the SmartNIC that they design, which has a bunch of interesting functionality. And Pliops is also doing the same, but for storage. So in a way, they implement some of this glue that we basically had to implement in GPU, and they are accelerating that in hardware, but still taking advantage of GPU access to that. So yeah, I believe that this is pretty real.
Okay, thank you. Timo?
Yes. So first, thank you for this very nice talk. I really enjoyed it. I have one question. You had one slide where you did this remote copying out of data, basically, and from, I think it was from the at the point where you did it with the SmartNIC, and you said you have like a custom doorbell mechanism to kind of
Yes.
signal which pages are ready, basically, right? Or readable. So how does the memory model work at this granularity? Is this somewhere documented by NVIDIA that, okay, you have this instruction to say this page is now not in some write buffer, but is actually in memory and you can DMA it out? Or is this automated that if the page is pinned or registered as in use for DMA, then things will not be buffered? How does this work?
So I'm trying to understand what you're asking specifically. I mean, at the conceptual level, the GPU here does not basically it exposes the RDMA buffer, right? So RDMA buffer of that GPU is managed by the CPU.
But of course, I want to write to this buffer from my accelerator as well, right?
Yeah, so if you want to write to this buffer by your accelerator, you do that, but then you basically use some, you basically write a work queue element the way you want, because all this green, I'm not sure if you're seeing my pointer, but
Yeah,
all
I
this
see it.
all this green area is entirely custom made, right? So I do that the way I want, and the parsing is done by this orange guy here, right? So the ARM processor is accessing this area, and it can, because it runs the code that I want it to run, it does exactly what I want it to do. So for example, I can build my own format of the work queue and let the ARM processor figure out how to read it and what to do, right? So
That I understand, but
that becomes very efficient. Yeah.
my real question is, if I write something in a GPU kernel to GPU memory, how can I make sure that, okay, now this actually lies in memory and is not cached in some write buffer or
Right, great.
some GPU internal
Perfect.
cache? Because
Yeah.
for x86, we have a defined memory model. I don't know that something exists like this for NVIDIA GPUs.
Right. So fortunately, the GPUs today maintain C++11 memory model. And there is a pretty elaborate discussion about that in my lectures that I'm teaching. But I can send you the slides later if you want.
That would be very nice.
Yeah, absolutely. So, but in addition to that, there is a little bit of hackery to make sure that the NIC does not read outdated data over PCI. And indeed, there is a little bit of some hacks to be done, but it's possible and actually usable.
Yeah, cool. I would be very interested in those hacks.
Sure, absolutely.
Thank you.
You should read this paper because most of that is there.
Okay, thank you.
Mm-hmm.
Cool, thank you. We have one question from Torsten in the chat. How do you work with industry to get access to the low-level aspects of hardware that you need for your work, driver interfaces, etc.?
The truth is that we don't really work with industry at that level. So we ask people around. We have friends in NVIDIA, and one disclaimer: I'm on sabbatical in NVIDIA now, but nothing that in the slides here represents anything from NVIDIA or any work that I've been doing just for the last 3 weeks there, because all of that is dates way back to 2022 and 2023. Anyhow, my point is that we actually use some open source, and then we hack and we ask questions. And as a matter of fact, these days, the situation is much better. So you have open source drivers for an AMD GPUs. You have the entire compute stack for AMD. You have a lot of drivers open sourced for NVIDIA NICs. So it's not too bad.
Thank you. Thank you.
Thank you. I think it seemed like we have answered all the questions. So thank you again, Mark, for your presentation. It was great to have you.
Pleasure.
And have a
Thank
great
you very
rest of
much.
the day.
Thank you. Bye-bye.